Good day and welcome to part 1 of our discussion on antiderivatives. We will use this discussion on antiderivatives to transition from the definition of the definite integral, which we've been working through in our previous videos, to using something called the fundamental theorem of calculus, our next topic of interest, to quickly and efficiently evaluate definite integrals. In order to use this so-called fundamental theorem of calculus, it turns out we need the concept of an antiderivative. So let me start off with just kind of a motivating scenario. A physicist may know the velocity of an object and would like to determine its position. Or similarly, a biologist might know the rate at which a population grows and would like to know its current size. And both of these statements or questions are really getting at the same idea. If you are given a function little f, think it's the velocity or the rate of growth of the population, can we find a function big F whose derivative is little f? That is, stated slightly differently, big F prime is equal to little f. And this is precisely what it means for big F to be an antiderivative of little f. So we say that big F is called an antiderivative of little f if big F prime is equal to f. So as the name suggests, antidifferentiation is going to involve undoing a derivative. Starting with a function little f, can we find this associated function big F whose derivative is that original function? And the good news is that we have extensive experience this semester working with differentiation, and we should be able to put that knowledge and intuition to work for us. And with that observation in mind, I would like you to pause the video for a moment and see if you can answer this next question. Can you find an antiderivative of cosine x? That is a function such that when it is differentiated, you get back cosine. And I find that this question usually leads to really good conversation in a calculus class. So hopefully you're looking at this and saying, well, of course I know an antiderivative. How about the function sine of x? So note, if big F of x is equal to sine of x, the derivative of sine x is equal to cosine x. So in this case, yeah, absolutely. Sine of x is an antiderivative of cosine because the derivative of sine is equal to cosine. But could you come up with any other antiderivative? And hopefully after thinking about this for a moment, we might be able to come up with an example. The reason being, we know plenty of functions whose derivative is 0. That is to say, what if you considered just a vertical shift, something like sine of x plus 1? Or even more generally, what if big H of x was simply sine of x plus whatever your constant of choice is? And in this case, c can be any constant. And as we will see in a few minutes, this function h of x would be referred to as the most general antiderivative of cosine, and any antiderivative has to be in this form. But to get to that point, let me just make an observation. If two functions have the same derivative, for example, big F and big G above, the derivative of both of those functions is cosine. Then how do the functions themselves have to be related? Well, it turns out it's exactly what we see above as well. Then f of x must be equal to g of x plus some constant c. And we can give a very quick, easy explanation as to why this is true, so I think it's worth taking the minute required to do so. And in order to convince ourselves that this is true, we simply need to consider an auxiliary function. So if we consider the function h of x, which is equal to f of x minus g of x. And all we're supposing at the moment is f prime is equal to g prime. And from that, we want to make this conclusion. So for this function h of x, if we could show it must be equal to a constant, then we're done. So what is its derivative? So h prime of x would be f prime minus g prime. And our assumption is that f prime is equal to g prime. And if two quantities are equal and we subtract them, we of course get back 0. And earlier this semester we encountered something called the mean value theorem. And the mean value theorem told us that if the derivative of a function is ever equal to 0, the function itself must be a constant. So I'll just note, more or less for fun here, that by the mean value theorem, we must have that h of x is equal to a constant. But we defined h of x above as being f minus g, so if we just complete this, f minus g equals a constant, so f of x is equal to g of x plus c, which is exactly what we were hoping to show. And this leads us into the concept of the most general antiderivative. If big F is an antiderivative of little f, then the most general antiderivative of f is big F of x plus c, where c is any arbitrary constant. And any antiderivative of little f must take this form. So with this in mind, let's see if we can find the most general antiderivative of the function 2x. And I'd like you to pause your video and take maybe a minute or so and write out the most general antiderivative. And hopefully at this point you have done so. Now if you're struggling to kind of come up with an antiderivative, let me write this slightly differently. Can we find a function big F of x with the derivative of big F equal to 2x? That is, what function, when differentiated, gives you back 2x? And there's immediately one function that comes to mind, x squared. Now note, x squared is an antiderivative, but there are many more possible antiderivatives. The most general antiderivative is when we add in a plus c, where c is representing any possible constant. So this is the most general antiderivative. And from here on out, whenever we're referring to antiderivatives, it will always be assumed that we want this most general antiderivative, so the plus c should be included every time we antidifferentiate. And I do want to illustrate kind of what's going on graphically. Having this plus c really means that we have a family of curves. And what I mean when I say a family of curves is that there is one curve corresponding to each value of that constant c. So one curve for each value of c. And just to illustrate this graphically, when c was equal to 0, we had just the graph of x squared, which is an antiderivative of this function 2x. But of course, we could add any constant we would like to this. For example, we could have y equals 2x x squared plus 2, Or you could even add a negative constant to this just for fun and maybe say, how about x squared minus 1? There are infinitely many antiderivatives, one corresponding to each value of the constant c we could add to x squared. Now, luckily when it comes to antidifferentiation, it has a very clear connection to our previous discussions with differentiation. In fact, as they are in a sense kind of opposites of each other, antidifferentiation undoes differentiation, corresponding to our rules of differentiation should be rules for antidifferentiation. So with that in mind, let me complete what we can think of as being a table of common antiderivatives. And for this, we will let big F be an antiderivative of little f, and big G be an antiderivative of little g. So if we start off with a function in the left column, its antiderivative is going to be written in the right column. So if the function is c times little f of x, an antiderivative would be c times big F of x. If f plus g are added together, the antiderivative would be f of x plus g of x. And I'm going to come back to this third row in a moment. Let's first work through the trig functions. So an antiderivative of cosine, as we've previously mentioned, is sine. And note I'm just writing down an antiderivative, but all of these would include a plus c as well. Typically with the table of common antiderivatives, we leave that plus c off. So working through this, what is a function whose derivative is sine? And immediately we might think cosine, but when we differentiate cosine, we get minus sine, so that's actually minus cosine. The derivative of tangent would be secant squared, and the derivative of secant is secant tangent. And undoing those ideas, we have these two related antidifferentiation formulas. The last part I want to add in is an antiderivative of x to the n. The antiderivative, I'm going to write it down and then we'll verify it, is 1 over n plus 1 x to the n plus 1. And since we're dividing by n plus 1, we do not want n to be equal to, and I have a small typo here, there should be n should not be equal to minus 1. And just to verify that this is true, when we differentiate 1 over n plus 1 x to the n plus 1, this 1 over n plus 1 is a constant and can be pulled in front of the derivative. And the remaining derivative is x to a power. So the power rule of differentiation tells us the power comes down front, and the new power of x would be 1 less than previously. And in this case, the n plus 1 over n plus 1 cancels off, and the x to the n that we're left with is precisely the function we want it to be. So consider this for now to be our table of common antiderivatives that we should be familiar with and we can use quickly and efficiently. In our next video, we will explore several common examples of calculating antiderivatives. So stay tuned and take care.